15. And the name of the chapter is the Baire's Theorem, and it's theorem, and its consequences. This is what we're going to do. We're going to Baire's theorem, and we're going to essentially prove three consequences of the Baire's theorem, so-called uniform boundedness principle, whatever that means. Boundedness principle, and open mapping theorem, and closed graph theorem. Okay, so like these three theorems are called the big threes. Big three theorems of function analysis. Big threes, some people call it. Okay. Baire's theorem is not really a result in function analysis. It's kind of more specific result in metric spaces. So what we're going to do today is that we're going to at least do the Baire's theorem. It's just pretty simple result. The fun result. So, what does the Baire's theorem is telling me? So let omega d be a complete metric space. Okay, and let an be a sequence of closed subsets, closed as in subsets of omega, such that their union, countable union, exhausts whole of the omega. Okay. Then there must be a natural number and a point in omega such that if you take that x and draw a ball of the radius r for it, okay, is going to be contained in that A and N. Okay. It seems not something too much interesting result, but it has somehow pretty nice consequences actually. So what does this result is? And I mean, okay, frankly speaking, this is not really the original statement of Baire's theorem. Okay. That says something else, but that also follows from this actually. We're going to do some exercises, in which we'll do the original version of the Baire's theorem, which actually says roughly, if I give you the key statement of that says that if you have a sequence of open sets which are dense in a complete metric space, then their intersection of open sets is also going to be dense in a metric space. So that's what simply. So intersection of open and dense subsets in a metric space is also open, obviously, but it's like a countable intersection, obviously. So countable intersection of open and dense subspace of metric space is also dense actually. So that's what the original version of Baire theorem is, but that also follows from here. Okay, we're gonna see some exercises. But for proving these results, we don't need that result. We need this version of the result actually.
Sir,
Essentially.
for every ball of radius, मतलब R कोई भी
No. What does it say is that if you have a sequence, a countable sequence, obviously sequence is countable of closed sets whose union is omega.
Okay.
Then you can find a specific n. Out of all these open closed sets, you can find one closed set and a point, a unique point in x actually, omega, such that when you draw a ball on that point and
of any radius
of any radius,
okay.
maybe some radius, is it any radius? So I need to, not any radius, but specific radius actually. Some radius, such that the open ball is contained in an. Probably better would be to call it an star actually, so that we will not assume that n is abstract. Maybe saying that a specific m, such that this ball is contained in n. So in other words, what this theorem is telling me that if I have
for every x in omega, there is
not for every x in omega. That's what the key thing is. So what I'm saying is that imagine I have this space, okay,
Yes.
and I can exhaust this space by closed substructure, okay, roughly something like that. Their union is covering everything, okay. Then it says that if this whole space is a metric space, out of all these closed sets, there must be a closed set in which you can draw a ball, okay? You can find a point and draw a ball around it, and that ball will be entirely contained in this specific closed ball.
Sir, but I am getting if I know कि मतलब जो हमारी स्पेस है उसके अंदर कोई भी हम बाल किसी पॉइंट पे डाल वो किसी न किसी सबसेट में होगा, क्या ऐसा नहीं हो सकता?
That's what now the theorem is saying. Whether that will be true or not is a different discussion. Maybe, but there will be at least one ball which is contained in a specific closed set actually. Okay. For proving this, I would like to prove a lemma. A version of that lemma, we proved it in real analysis. So it's just a bit abstract version of it. It's not something much difficult. So it's so this this result will be just a simple corollary of this lemma actually. Okay. It's called the principle of nested balls. Principle of nested balls actually. Okay. What does the lemma say? Omega d is complete. Okay. And let I have a sequence of open balls, closed balls actually. Bx1, R1 contains Bx2, R2. I hope we understand this, the difference between the notation actually.
Open.
Okay. And this contains Bx3, R3, and so on and so forth. So it's a decreasing sequence of closed balls. Okay. Vn. Okay. Then if Rn goes to 0, in other words, if you keep on reducing the radiuses of these nested balls, then the intersection of all these balls is going to be a singleton.
X.
And such that the xn Rn would be a singleton. Okay, so we need to find that such an x exists. Okay, and this x must be unique. In other words, in this set you can't have any other elements. Okay, is it making? Do you remember something like similar? So there we did with the closed intervals actually. Okay, so like a closed interval within closed interval and the intersection of all closed intervals gives you 1 point actually. So it's just a slight generalization of that. Okay. So here's a proof. Here's a proof.
One thing is x is the limit of x and this sequence.
Is it written in the theorem? Oh yes. Where x is the limit n goes to infinity of xn. In other words,
This limit is ensured
yes, this limit is ensured.
by R.
Okay.
So what can you say about open balls?
Hmm?
What if we had open balls?
You can't have such a result for the open ball. Maybe you have, but I'm pretty much skeptical that you can have something similar with the open balls. With the finite case, we know that the only finite intersection of open sets is open actually, not even a countable. So I can give you some countable open sets, open sets, countable collection of open sets, and their intersection is not open. Okay? So obviously you can't expect this result for open sets actually. But yes, for closed sets, you can do. Well, would be very interesting to make a picture of it actually. What would be, how does the picture of this would look like actually? Just think about it. So I have a ball with the center x1, and then I have another ball with some center x2, and I have another ball with the center x3 and so on and so forth, and somehow we are saying that these axes are going to get cleared.
यहाँ पे सेंटर सेम है
हाँ?
सेंटर सेम नहीं
सेंटर सेम नहीं है
So
सर।
next to is three
केनी
different.
सेंटर
Sequence.
Yeah.
वो तो डिग्री ना है तो समझ सकते हैं
Anyway, so let's quickly sort this out. It's a very simple proof. Let's deal with the first uniqueness. Otherwise, there will be at most one such element. So we know that x is only there. So x is there. So assume that the intersection contains x. But assume that there is another element in this basically intersection,
And that is x.
and then I'll show that that would be equal to x. So both would be.
Sir, why x is there? I didn't get this.
No, I mean, okay, so first I'm proving uniqueness. So imagine there is x,
Okay.
okay, and then I'll prove the existence that there must be some x actually there. Okay? So I'm doing the first uniqueness proof. So let y is in ball of xn Rn for all n in nx. Okay? So that's another element. Okay. Then obviously the definition tells me that the distance between y and x is less than or equal to Rn?
Yes.
Yes, sir.
Agree? And what does this mean? I know that this Rn goes to 0, Ln goes to infinity.
Means y equal
This
to-
means that xn converges to y as
Yes.
n goes to infinity.
But x is to x.
But xn also converges to x actually. And the limit is unique, hence x must be same as y. So you can't have more than one element in this intersection. So let's do the existence proof actually. Okay. Now let us give it, let us we have an epsilon positive and let's try to find an n, a natural number n, such that our n is less than or equal to epsilon by 2. Can I find such a n actually? Why such a n must exist? Just think about it. Rn is going to 0. So Rn is going to 0. So I can make Rn closer to 0 as much as I want actually. Okay? As much as I want. So if the epsilon is parameter, okay, and I want to make this Rn to be smaller than this epsilon actually, I can do it. I can find an instant. After that instant, the radius, or maybe r, evaluated at n is less than or equal to epsilon by 2. So this is not something, this is not something unusual. Now, if I take n and m bigger than or equal to this capital N and consider, alright, so what first I would like to show, essentially what we need to show actually. So we need to show that this limit must exist. This must converge actually. This limit must exist. And for the convergence, since I'm in the complete space, I need to show that this sequence is a Cauchy sequence. Okay? This sequence is a Cauchy sequence. So that's it. So for n and m bigger than or equal to m, I would like to consider a Cauchy sequence dxn, xm. I can estimate this by
triangular inequality.
dx in x
dxn x plus d
x
xm x actually.
both are epsilon by 2.
Both are less than or equal to
Epsilon by
epsilon by 2 plus epsilon by 2, which is epsilon.
Cauchy convergence.
Okay? And this implies
xn is
Then-
Cauchy.
xn is Cauchy actually. And hence limit n goes to infinity xn equal to x exist. Okay? X defined as a limit exists. That's not a problem. Now, what would be the remaining thing only? The only thing that is remaining now is, shall I get rid of this actually? The only thing remaining is why, okay, here's the thing. Why this x must be in the intersection of balls actually. This x. We give an argument. Okay, we know that this limit exists now. But why this limit must be in this intersection?
Because it is content in sequence of bars.
Huh?
Bars एक दूसरे को content करें, हम उसमें से pick कर रहे हैं तो Baire उसमें होगा.
So the ball contains the sequence. I'll write it precisely. The terms of the sequence, and the balls are closed actually.
Close bars.
So they should also contain.
Limit.
Let me put it precisely. For any n you choose from n, okay, the ball bxn Rn contains how many terms? Contains
In terms.
xn for all n bigger than or equal to n. So it's like after n, all of these terms are there. Are you getting the point? And hence what? So if this is the case, the sequence is convergent, then this limit must also be
In this one.
as ball is closed,
Limit of xn.
so x must also be in bxn Rn, and you can choose this capital N no matter what you want actually. Okay? That's it. We're going to do the Baire theorem. Finish the Baire theorem in the next class. It's just a two-liner proof. Is it making sense?
Yes, sir.